This lecture will describe the Van Hoff equation, the relationship between the equilibrium constant and temperature. And remember, we've encountered Van Hoff before. Van Hoff is the one that talked about the Van Hoff's factor when we had ionic solutes in colligative properties. It's the same chemist. Okay, we've developed two equations here, right? We've got that delta G0 equals delta H0 minus the temperature times delta S0, right? We've also done delta G0 equals minus gas constant R times temperature times the natural log of the equilibrium constant, right? And so we can put those two equations together. That minus RT times the natural log of the equilibrium constant is equal to delta H0 minus T delta S0. Right? Now, if we want to get temperature all on the same side, what we can do then is divide both sides by minus RT, which is going to give us then on the left, right, just the natural log of the equilibrium constant. And then on the right, we can divide that up so we can have delta H0 divided by minus RT minus T delta S0 divided by minus RT. Right? And if we do that, right, a negative divided by a negative gives us a positive, and temperature divided by temperature is 1. And so we can sum this up as the natural log of the equilibrium constant is going to be minus delta H0 over R, 1 over the temperature, plus delta S0 over R, right? And if we look, this is an equation of the form we've seen before. Right? So here's our three equations we've encountered that follow that same pattern, right? The Clausius-Clapeyron equation related the vapor pressure to the enthalpy or the heat of vaporization, right? We had the natural log of the vapor pressure, heat of vaporization over R, 1 over temperature. We had the Arrhenius equation that related the rate constant to the activation energy and the temperature. And now we have the Van Hoff equation that expresses a relationship between the natural log of the equilibrium constant and the standard enthalpy for the reaction and the reciprocal of the temperature. And so as we see here, this is a linear form of the equation, right? So if we would plot as our x variable 1 over t, as our y variable the natural log of the equilibrium constant, then minus delta H0 over R would be the slope. And in this case, our y-intercept would tell us something about the standard entropy of our reaction. Right? So with the Van Hoff's equation, right, in a laboratory what you would do is you would determine equilibrium constants for a reaction at a number of different temperatures, right? And you would plot 1 over temperature in 1 over Kelvin, right? These have to be Kelvin temperatures, versus the natural log of the equilibrium constant, you would get a line with a negative slope, right? You'd have individual points, and you would have a line with a negative slope where the value of that slope is equal to minus delta H0 over R. And if you extend your plot to the y-intercept, or as the equation does, right, the delta S0 over R is equal to the y-intercept. Okay? So, right, might there be some data that you have to plot as a result of this equation? Certainly. But we also know that, right, in general chemistry, even though it's not as useful scientifically, in general chemistry we develop a two-point version of these equations to work general chemistry problems, right? So let's look at the two-point version of that Van Hoff equation. So if we have two equilibrium constants, K1 determined at temperature 1 and K2 determined at temperature 2, right? Then we can take the natural log of K1 minus the natural log of K2. And that's going to be equal to minus delta H0 over R times 1 over T1 plus delta S0 over R minus delta H0 over minus a negative delta H0 over R 1 over T2 plus delta S0 over R. Right? All I did was take this equation twice, right? This minus the second condition, this minus the second condition, right? But if we go through that, one of the things we notice is that, right, if we look at, we have this term minus that term, right? That goes to 0, right? So those two terms take themselves out of our consideration, right? And so now we've got this minus delta H0 over R in both terms, and so we can bring it out in front, right? And the other thing we can consider is that when we subtract logs, that's the same as dividing. So this is going to give us the natural log of K1 over K2, right, equals minus delta H0 over R. But since we brought the minus out with this minus, right, that's going to make this one plus, this one still minus, right? And so you end up with what happened to us before is the temperature that goes with the second condition ends up first, and the temperature goes with the first condition goes second, and there we have a two-point version of our Van Hoff equation that we can use. So I'll put together a different discussion where we'll do some problems with the Van Hoff's equation.